Now let's see what is a data type called parameter. In Verilog, you can store a constant value in a module by using a keyword called parameter. Okay, it will store a constant value, or you can call it as a initial condition value whenever you want to. Why it is required? Let me tell you an example. Let's say I want to store a parameter. Let's say I want to store a parameter which is always constant, like pi. Pi is always constant of 3.14, right? So I can define this pi as 3.14, or I can define a parameter. Let's say my clock time period TP is equals to 10 nanoseconds. So why do I do this? Whenever I'm trying to generalize my clock period. I can directly give my clock period is equal to 10 nanoseconds. But if I give it to a constant called TP, whenever in the later state of coding, I can directly change my TP to 20 nanosecond or 30 nanosecond. That will be get affected to the entire program wherever I use this parameter TP. Maybe in the later stage of code, I will assign this TP for my clock time period like this. There, here if I change this value, that change will appear here and it will modify my code. So that is the purpose of parameters. There are different things like def parameter and local parameter, which are some advanced concepts. I will describe them when I describe you the advanced concepts of Verilog. Okay. This is about these parameters: integer, real, time, and parameter. Now let's see what is an array. Okay, we have seen the vectors. Now we are seeing array. The first difference you need to understand between vector and array is the way they define, right? In case of vector, you will define like this: range of some 7 down to 0 of data. But in the case of array, you define like this: range of data 7 down to 0. So what does this mean is, this is a 7-bit vector. The data is a 7-bit vector like this. 7, not 7, 8-bit vector from 0 to 7. 7 is the MSB and 0 is the LSB, right? We know the leftmost part is the LSB. But this is a definition of array. How does this look is, it is having a single bit value of 8 different values. Data 0, data 1, similarly data 7. So these are a single bit registers with 8 different values like this. And this is a single vector with 8-bit value. So you understand the difference between vector and array, right? This is a one-dimensional array. You can define 2-dimensional, 3-dimensional, whatever dimensional array you want. Let me show you an example. So as I told, you can define multiple dimensional arrays like this. I want to define an array of integer of a matrix. How much? 4 down to 0 and 0 down to 255. So what does this mean is, it is a 2-dimensional array matrix. If I want to define a 4-dimensional array matrix, I can do like this: register which is having a 64-bit data of matrix 4 dimensions like this: 15 down to 0, or 5 down to 0, second dimension, third dimension is 6 down to 0, fourth dimension is 255 down to 0. So this is how you can define a 4-dimensional matrix of width 64-bit. Okay. So there are multiple ways you can define like this: integer I 0 down to 8, register 7 down to 0, port ID. See, I am using a comment here. This double slash is a comment. So what does this mean is, an array of 4 port IDs, each of 8-bit value. So reg 127 down to 0, array of, this is a 3-dimensional array. As I have written, this is a 4-dimensional array. And wire 7 down to 0, WL 15 down to 0, this is a 16 array of 8-bit vector wire. And let's say I want to define a 2-dimensional array of single bit wires. So here I am not defining any width. So by default, it will take it as a single bit. So this is a two-dimensional array of single bit values, single bit wires. Okay. So uh, let's take one example where you want to assign value to the array. Okay, how to assign values inside the array. So you can directly call like this count. Let's say if you have defined an integer array of count 16 bit. Okay, once you define a count of 16-bit array, you can directly call count of 8 is equals to 0. So what does this mean is it will assign 0 to the 8th bit of the counter, 8th bit or 8th element of the counter. Okay. Next, you can do a 4-dimensional array assignment, a 3-dimensional array, let's say this array, a 3-dimensional array like this. Array 3D of 0th dimension of 0 of 0 of, let's take, I want to assign 7 down to 0 is equal to 0. What does this mean is it will clear the 8 bits of the register that is accessed at 0 position. Okay. There are some illegal syntaxes that you should not do while assigning arrays like this. Let's say your port ID, take this example where you define the register of 7 down to 0 with port IDs 0 down to 3. Okay. So what is it? It is an array of 4 port IDs which is having 8-bit width, right? So you cannot define assignment like this. Port ID is equals to 0, which is a illegal assignment because you are trying to attempt to write the entire array with a single value. That is not allowed in Verilog. And matrix, let's say this matrix or array that I have defined here, array of 1 is equal to 0. This is also an illegal assignment because here it is having 3 dimensions, but you are only assigning to the 1-dimensional value. So you need to avoid these kind of illegal statements to properly assign arrays. Now let's see the last data type called strings. Strings are very similar as in case of C language where it can be used to store in a register, right? The data is stored inside the register. The width of register should always be greater than the length of the string that you want to write. Otherwise what happens? It will truncate the leftmost values of your string. If the length is greater, then it will add zeros to it. That doesn't be a problem to you, right? But if the length is small, then it will truncate the values. So always take care the width of the register should be larger than the string that you want to assign. So let's take an example. Register of each bit, each character takes 8 bits. So I'm multiplying 8 into how many characters I want. Let's say I want to write a string of Verilog. So I need at least 1, 2, 3, 4, 5, 6, 7. So just for in case I'm assigning at least 9 characters down to 1. So this is my string. I want to write string. string string. Now I'm initializing my process and I'm writing the string, my string, let's say. My string is equals to double quotes Verilog. This is how you can define a string. Always end with semicolon. There are some special characters like this slash n, which is used to get the new line, or slash t, which is used to get the tab space, which is very similar to C language, right? So this is about data types in Verilog. Once you are familiar with data types, we will move to some system tasks in Verilog, which are very useful to debug your program. So I will explain theory here, and later I will show you practically how to use this system task. There are 4 main system tasks like $display, $monitor, $stop, and $finish. Let's see the functionality of these things. The $display is used to display the information of different parameters like this P1, P2, Pn. So how to use the dollar display? If you want to display a parameter called display a string, you can display the string by using dollar display on your program. Okay. So there are some string format specifications for this dollar display. Similarly, in the case of C language also we have, right, this percentage %d will define the display variable is a decimal. If it is a percentage %b, then the display variable is a binary. Percentage %s means the display variable is a string. Percentage %h, the display variable is a hexadecimal value. Percentage %c means ASCII character. Percentage %m is the hierarchical number if you have any hierarchies in your module. And percentage %v is the display strength. If you remember, we talked about the strength, right? Strong, weak, full, medium and all. If you want to display the strength of any wire or resistor, you can use percentage %v. And percentage %o will give you the octadecimal value. And percentage %t means the time format. Percentage is the real numbers in scientific notation. As I told, the Verilog supports both scientific notations as well as decimal notation. Like this, if the number is 310, then you can use percentage %e. And if you want a decimal point, then you can use a percentage %f, which is a float value. Like this, 2.13 or anything decimal values, you can use percentage %f. And finally, percentage %g is a number which will which is a real number in scientific or decimal number, which is shorter format. Okay, these are the different string format specifications that are available in Verilog. So let's take an example of displaying a display function. You can write display dollar display and then dollar time to display the time of your simulation. We'll see these once we do the practicals. Okay, this is about display. Now let's see what is a monitor. A monitor is also a keyword or system task function. Keyword is monitor, but the system task function is dollar monitor. Okay, remember this thing. If you want to call any system task, you need to add dollar before that keyword. So let's see what is a monitor function will do. How does it is different from display? You can see the words display and monitor looks similar, right? But the functionality of display is different from functionality of monitor. The monitor will monitor your signals. In the case of display, you can use wherever you want to display that variables. But in the case of monitor, you just need to write once, and whenever there is a change in the signal will happen, then the monitor will give you the output. That is the main difference of monitor and display. Let's take an example. If you want to monitor a signal called monitor my clock, right? You can write like this. So what does it do? It will monitor your clock all the time. Whenever there is the change in clock, it will display that information on your screen. So you can use some functions like monitor on and monitor off. By default, when the Verilog code starts, the Verilog HDL tool will assign monitor on function. What does this mean is, wherever there is a monitor statement, it will automatically on. But if you want to control monitor on and off, you can use monitor on and off statements. Within this, you can write your lines of code where it will show the monitor thing inside the monitor on and off. If you want by default, you don't need to specify these two things, then Verilog will start the monitor function from the start of the code. And if you have multiple monitor statements on a single variable, the latest one will be will be displayed, not the previous one. Okay, remember these things. So we'll see how to use the monitor once we do the practicals. And the function stop and finish will have importance, like the stop is used to stop your simulation for particular time in the when the simulation is running. If you put a keyword or system task function called stop, then your simulation will be stopped and it will display the information, display the parameters or whatever you want to display, it will display, and finish will truncate your entire program. We'll see their use once we do the practical. Okay. Now let's see what is module and ports in Verilog. The module and ports definitions are very important in Verilog HDL because as you know, the module is one of the basic building block of Verilog HDL, right? In order to define any hardware description language, any uh, any circuit in HDL language, you need to define in terms of modules. So let's see what are the different components that are present in module, and we'll see an example. So the module definition always starts with a keyword called module and ends with end module. There is no space between end and module. So remember, the module definition starts with module and ends with end module. In between these two lines, you need to write your line of code. So the module name, comma, port names, port list, and parameters. These things should come in definition of module. Okay. Once you define the module, then you will write the port list, port declaration that are present inside the module. Okay. After that, you have 5 different components that are present inside the module definition. Let's see what are those. The 5 different components that are present in module are, first one is, so your Verilog code should look like this. First, it will have module definition where you need to define the name of module, comma, port list. What else you will require? Port declaration, and if you have any parameters, define them here. Once you define the module definition, then there are 5 important components that are present in module. They are declaration of wires slash registers. This is first one. Second one is register or any other variables. And second one is data flow statements. Third one is instance of different low level modules. Low level modules. Low level modules in the sense the leaf cells are the modules that are called from the top level modules. And fourth one is always and initial blocks. I will define what are always and initial blocks when I talk about behavioral or algorithmic level modeling. Okay. And the fifth one is if you have any user defined tasks and functions. After these 5, you will write end module. So a typical Verilog code will look like this. First, you start with module definition, which consists of module name, port list, port declaration, and parameters. After this, you will declare the wires, registers, or any variables that are required in this code, and then the data flow statements. Then you can instantiate some low level modules. Then you can use always and initial blocks, and then if you want, you can use some system level tasks and functions. Finally, you will end your code with end module. So this is one module. You can put as many modules as in a single file of Verilog. Like I can put module D flip flop and end that module. I can put module T flip flop and end that module. Similarly, I can put any number of modules in a single file. Okay. So let's see an example How does a module looks like? For this, I took a circuit called SR latch. The SR latch will look like this. This is S bar, this is Q, this is Q bar, and this is R bar. One of the input is connected from here. One of the input of this is connected from here. Right? This is a latch circuit. Remember what is the purpose of latch? It will store a 1-bit data. Right? So I want to write a module for this SR latch, which by using data flow statements, like by using two NAND gates. I require two NAND gates, right? So how to do that? First thing is I have to define my module. Here my module is MOM, module SR latch. Once I define the module, I need to define what are the different ports that are present in this module. The ports are S bar, R bar, Q bar, QB. No, this is Q and this is Q bar, right? This is Q and this is Q bar. These are the different ports. Once the port names are declared, I can define what are the port declarations. So I am commenting this port declarations. How do I declare? The Q and Q bar are output ports. So I am writing output Q comma Q bar, and S bar and R bar are input ports. So I am writing input S bar comma R bar. So this is called port declaration. Once the port declaration is done, then you can start writing the behavior or the hardware of your module. So I am using two NAND gates. So I am writing like this: NAND, which is a keyword to represent the NAND gate in Verilog. I am calling with name N1, and I am assigning the NAND of output Q, comma input S bar, and other input is coming from Q bar, right? Q bar. This is one NAND gate. The NAND gate output Y, input A, B. So in Verilog, we will first write the output node and then we will write two input nodes. That is what I did here. First I wrote the output node Q, then two input nodes S bar and Q bar of this NAND gate N1. Similarly, we will write NAND gate N2 as NAND N2. The output is Q bar and the input is, one of the input is Q and other input is R bar, right? So now my entire circuit definition is done. I have defined my circuit name, I have defined the ports, and I have defined the operation or internal blocks that are required for this circuit. As you can see, I have not used all the 5 components that I have described earlier in this module, right? I have only used the instantaneous of leaf modules or internal blocks, and I have used port declaration, but I haven't used tasks and functions, or I haven't used any assign statements, or I haven't used any initial and always blocks. But still, my module is complete and the circuit will run. So the 5 components are optional ones. I mean, you can write any module without those 5 components as well. We'll take one more example, then it will be clear to you. So in this example, I was trying to simulate the SR latch that we have defined earlier. In order to simulate the SR latch, what you need to do, you have to write a test bench to it. I am calling the test bench as top module, and I am calling this SR latch, I am instantiating this SR latch in this top module, and then I will verify by applying some signals here, right? This is the purpose of this example. So how to write module or how to write the test bench for this? Again, we will start with module and then name of the module, which is top, right? I want to define a module name top, and directly I will use the semicolon. See, I am not defining any port names or port declaration, because my top module doesn't have any ports, you can see. So I'm not defining the port names, and if I'm not defining the port names, I don't need to define port declarations also. So once I define the module name, now what I need to do, I will take two wires, wire Q, Q bar. Notice that I am writing Q and Q bar in small letters here. Wire S set and reset. These are my two inputs that I'm going to apply for my SR latch. And then I will call my SR latch that I have defined earlier. The name of the SR latch that I have defined is module SR latch, right? So same name I need to use here, module SR latch. And I'm calling with S1. You can give any name here, S1, S2, S3, doesn't matter. You're just calling that module with your own name here. Module S1. Then you will assign the ports whatever the order that you have defined here. Here you have defined S bar, R bar, Q, Q bar. So same order I need to define here. Set. Next one is R bar means reset. Next one is Q, Q bar. So Q means here small q and Q bar means small Q bar. Right? Now this module is instantaneous in the top module. After this, what you need to do, you have to apply the test vector. So how I am applying? By using a behavioral block. This is comment, so I am writing like this, behavioral block, like this. First I will initialize. So the statement initial will start whatever the lines that are come within this begin and end will get initialized when the program is called. Okay. So initial, begin and end, because multiple lines I want to write. I want to monitor the signal, so I want to use a monitor system test. Monitor the time of the simulation I want to see, and then I want to set is equals to 0 and reset is equals to 0 initially. Okay. Initially I will put set is equals to 0 and reset is equals to 0. Then after 5 nanoseconds, I want to put set is equals to 1, reset is equals to 0. After 5 nanoseconds, I want to put again set is equals to 0, reset is equals to 1. So by this way, I can give my input test patterns, and then I will end the initial block. Once I end the initial end block, I need to end the module also. So I am ending the module. So this is the complete test bench for this SR latch. Notice here I have not used any tasks and functions, but still it is a complete module. So the 5 components are just needed but not essential. Okay, they are optional. So this is about module. So let's see what is ports in Verilog. The ports are just like a IO ports, IO pins of a IC chip, right? Your IC has some IO pins. That is why that is how it will able to communicate with external world. So the ports in Verilog are similar to IO pins of your chip. You have design sitting inside this and you want to communicate with external world, you need a pins. Those pins are ports. So we will see what are the list of ports that are available in Verilog and how to define, how to declare the ports and how to connect the ports with external worlds and what are the rules that you need to follow. And then we will see how to exactly connect those ports to the external signals. Okay, let's start with list of ports. So in the previous example, I have shown a SR latch simulation, right? Now let's take an example of full adder, which is a 4-bit full adder. So this module name is full add 4. I'm calling it in a top module with inputs of A, B and C in and outputs of sum and carry out, C out. Okay, this is my top module and these are the ports. So how to write the port list? For internal module, module full add, which is name is full add 4. The port lists are A, B, C in sum S out. So we'll write like this. We'll first write the output sum C out, comma A, comma B, comma C in, and then close with semicolon. How to write the port list of top module? Module top. There are no ports. See, so I'm directly closing this. You understand? Now let's see port declarations in Verilog. There are three kind of declaration. One is input port, second one is output port, and third one is in-out port. We know what is input port and what is output port, but what is in-out port? The in-out port is like a bidirectional port. Let's say you have a D flip-flop here. If the output of D flip-flop is going to some other block, combinational block, then this output should no longer be a output port. It should be a in-out port because it is going as input to some other block. Similarly, if the input of D flip-flop is coming from some other combinational block, then this input port is no longer a input port. It should be a in-out port. That is the purpose of in-out port. Okay. So the keyword that you need to use for in-out port is in out. Okay. So the declaration of ports in Verilog is there are two types of declaration. The one way is as we are doing earlier, module and then write the port names sum C out A B C in, and then you declare the actual port declarations inside the module like this. My output is sum comma C out and my input is A comma B comma C in, right? There is one more way of declaration that is called ANSI C style declaration. In this, what you can do is here you need to write module name also. Don't forget that if you don't write the module name, you cannot call that module. So the module name is full add 4. So in ANSI style way of writing, the same thing if you want to write in ANSI way of style, then you need to write like this. Module full add 4. You can define the port declaration here itself. Output register, which is a register type, my 3 down to 0 sum comma output again register, which is my C out comma C. Since it is a 4-bit full adder, the output of sum is 4-bit and C out is a single bit. So I am not defining any bits to the C out. Similarly, input is also a 4-bit, so 3 down to 0. A comma B are 4-bit inputs and input C in, which is a single bit input. Close bracket with semicolon. Right? This is how you can define in ANSI C style. The ports, there is one important thing that I want to tell here is the port of type input and in-out cannot be declared as registers. Why? Because register variable stores values, right? But you want the input and in-out ports should act as immediately as possible. So if you define them using register data variable data type, then it is an illegal statement because you want the input or in-out port should start work as immediately as possible. So you should not define with register data type, you have to define with wire data type. If you don't define any data type, by default, the Verilog will take it as a wire data type. So that's why the inputs, I'm not defining any data type. So they are by default, they are taken as a wire data type. In this case, I want the output to be a register data types. That's why I have defined sum and cout with register data type. This thing is very, very important. If you understand this thing, then you will understand the rules of port mapping. Okay. Let's see what are the rules of port mapping. Let's say this is your module, and how to communicate with other external modules is this thing should be net inside the module, net or wire. If I write net, then it is inherently means wire data type. This should be net, or the inode port is net by default, right? That is what I explained now. Similarly, the input port is also a wire or net. It cannot be a register. The output port can be anything, either net or register. While you are communicating with other module, since it is going as an input to the other module, it should be definitely net, not a register. This is important thing you need to remember. You don't need to remember, just by seeing this you can understand, right? Since it is going as an input to other block, this should definitely be a net data type. Similarly, this is going as an input or inode port, this should be definitely be a net. And since it is coming from outside, so this may be output of some of the blocks, so it can be either register or net. Understand this thing? Since it is coming from some output block, so it has a flexibility that it can be either register or net. But these two things should definitely be net data type only. So you have option here either register net, and you have option here either register net. Remaining all the things should be net or wire, right? This is very, very important thing in Verilog, because once you start writing your code, it will always give you syntax errors if you don't properly match these port connections. We'll see them once we do the practicals. So let's take an example of illegal port mapping. The same example I will take the full adder. Its name is full add 4, and I am calling in a top block. So the module is module top, small top, module top, and my port declaration is register 3 down to 0, A comma B, register C in. You cannot write C in here. Why? Because the C in is a single bit value, whereas A and B are 4-bit values. So I am writing it in a separate line. Okay. Similarly, register 3 down to 0 sum, and wire C out. Now I am calling my full adder 4, which is the name of this module, with my own name ff4 or something. Then I am assigning sum cout A comma B comma C in, then semicolon. So this is an illegal port mapping. Why? Because you can see the sum I have defined as a register, which is wrong. It needs to be a wire. Why? Because you cannot have output port as a register in a top module. It should be a wire, right? This thing is very, very important. There is one more way where you can directly call without any ports like this. If I don't want to connect cout, then I can directly call like this: full add 4 ff5. Directly I will write sum comma, and then I will leave a space for cout. I don't have any port. Let's say I don't have any port that is named Cout in this top module. So I'll leave a space and then I will connect A, B, C in. This is legal, but this is illegal because you cannot write a register as a output port. So you have to define it as a wire port, right? So now let's see how to connect these ports to the external signals. So there is one thing called order. Either you can match the order of the ports or you can directly do connect by names. So there are two ways. One is matching the order and second one is connect by names. In matching the order, the same way that I am following in the previous slide, we'll call the top module. Inside the top module, I will call my full adder, full add 4, let's say FF, and then the order of the pins that I have defined here, the module full adder should match here. What order I have defined for my full adder? I have defined sum, Cout, A, B, C in. So the same order I need to follow here also. So I am following sum, Cout, A, B, C in. Okay. The other way is you can do by using connect by name. In this method, you can write like this: full add or FFCN, connect by name, let's say. First, you need to write the port name of the module that you are instantiating, right? The full adder module I am drawing again here. This is my top module. This is my full adder module. It has three inputs. Let's say small a, small b, small c in, and output is small sum, small c out. Okay. So first you need to call this thing, the internal one, dot sum, and then map it to the module name that is available in top module. I have defined in capital letters, let's say, then capital sum you need to map. Similarly, the small c out that is available in this module, you should first call it and then map it with your capital C out that you have defined in top module. Similarly, the small a that you have defined here should call mapped with capital A, and small b should be mapped with capital B, and small c in should be mapped with capital C in. Right? The advantage of doing this is you don't need to remember the order. Let's say here only the number of pins are 5. Let's say you have 50 or 100 pins. How do you remember the order? So in that case, you should follow this method where you will directly call the name of the pin and assign it to your own pin. This is very easy, and this is very easy to debug also. In future, if you have different modules, if you are calling with different modules, you can call with different names by calling first with module name and then top module's name, right? So this is how you connect the ports in Verilog. So finally, I want to show the components of a simulation. What is a design block and what is a stimuli block, right? Till now I am talking about two things, right? Internal block and top block. What does this mean is the internal block which I am calling in top block is a design block and the top block is a stimuli block. We will call it as a stimuli block. So once we do practicals, we will see how to use these in Verilog. So in the next coming video, I will describe the practicals of what are the concepts that we have learned so far. In this session, I will explain live coding on basic concepts of Verilog. So the contents are like this. First, we will start with the hello world program of Verilog, which is an example of system tasks that we have defined so far. System tasks. And then I will move to an example on operators that present in Verilog, like unary operator, binary operator, and ternary operator that we have learned so far. And then I will move to example on data types of Verilog. There are different data types like register, wire, right? All these data types we will see in this example. And then an example on concept of module. how to do the moduling, how to do the nesting of moduling, how to do the hierarchical modeling. All these things we'll see in this example. And then example on concept of ports, how to do the port declaration, what are the two different port declaration that we have learned, like port declaration by using order or port declaration by using connect by names. So we'll see that in this example. And finally, I will implement a ripple carry adder, which will use all these concepts that we have learned so far. So let's begin the practical session of Verilog, the basic concepts of Verilog like this.